Hello, everyone. I'm going to give sort of simple and brief introduction of what I think are the most important criteria for the future certification of quantum key distribution system. That's why I put here this forward-looking criteria, because despite some of the QKD systems are becoming commercial and are already on the market, there is not yet a wide deployment on the commercial side, so that we do not have yet the ultimate criteria for standardizing and certifying this technology. So we have to use a little bit of imagination to think about this criteria in the next future. However, we heard that there is a global deployment of QKD ongoing around the world. The Tokyo QKD network, this is not geographical, of course, Tokyo is here, but let's say just in the order of sort of chronological order. Then we heard about the impressive Chinese QKD network using satellites and the metropolitan QKD network. And there is, as you know, this ongoing effort here in UK for the quantum network between Bristol, London, Cambridge, and other cities. And then there are other attempts all over the world, in US and in South Korea and in Europe. Even if I don't include all the possible nations, there is definitely a wide deployment of the QKD technology. So that means that it's important to standardize this technology and also to certify the QKD systems in terms of key rate, security, and features that they can have, so that this allows interoperability of the systems, but also the next future certification of this technology. So speaking of standardization and certification, what is the process that we can imagine? First of all, there are some requirements, and this is somehow how the whole process starts, and these requirements need to be standardized. So the typical process we can imagine is that you have somehow something similar to the IT-related security that can apply to QKD systems as well. And then in this case, you have this common criteria framework in which you define a target of evaluation, that is, for example, a QKD system, and then there are some users asking for security requirements, and these are the requirements I'm talking about, and they file their request using a protection profile, so-called protection profile, and then the vendors try to implement this request in their security target, and then there will be some evaluation laboratories to evaluate if the security target has been matched or not. And then there will be certification bodies to certify somehow the security of the system that have been implemented. And I believe that Norbert Lukenas will say something more about this later on. However, if the requirements are there, then somehow the way to express these requirements is through standards. So a user cannot really express a requirement if you don't give a set of standards that the user can exploit to define the request. So for that reason, you have standardization bodies that enter the process. For example, the ETSI, the European Telecommunication Standard Institute, or the ISO, the International Organization for Standardization, and they start the process of standardization. And then for that, you need a consensus. You take a pool of experts, and they start discussing what the best criteria are to standardize the technology and then eventually to certify it. And then you define sort of objective criteria, and this is somehow the discussion that is currently ongoing for QKD. And when you have that, then you need somehow an audit to see if the requirements have been met. And for that, we can imagine there will be some accredited or not accredited certification bodies that will file an audit report, and then eventually a certificate will be filed by an authority. So this is a sort of common flow chart for certification in the ISO, for example. So we can imagine a similar process for QKD in the next future. So what is it that we have to certify? I'm going to state the obvious here, so I'm pretty sure that everybody in the audience know the cryptography problem, even because we had this beautiful lecture by Simon Singh that explained the history of this a little bit. So you want to have Alice and Bob communicating, and you want to leave Eve out of the communication. And this is quite an ancient problem, and currently we use public key cryptography to distribute keys and then symmetric encryption to make the communication confidential. And quantum key distribution is qualitatively different solution, and in this case we aim to obtain information theoretic security of the communications. So how does it work? In a cartoon, you have Alice and Bob connected by a quantum channel, for example, an optical fiber, and you start sending encoded single photons. And in the middle, Eve tries to intercept the photons, but she is limited by the laws of physics, so her interception cannot be 100% successful. So in this case, again, to say sort of well-known things, security is said to be unconditional because it doesn't depend on the computational power of the eavesdropper. And the QKD protocol itself, to exchange the information, is just a mathematical construction based on some assumptions and on the laws of physics. So it cannot really be broken because it's like a theorem that you demonstrate, and until the assumptions hold, this is just something that you cannot really break. What is more tricky is the QKD implementation. So in this case, we need to make sure that the theoretical assumptions are met in the practice, and this is clearly more difficult to verify and to certify in the practice. And this is basically what the problem is all about. You need to define criteria to make this process as smooth as possible, and to let people to verify that the assumptions are met in the real system. So, for example, it is usually assumed that Eve cannot access the user's boxes. Here, you typically put some locker. And is this a reasonable assumption? Definitely it is necessary because you cannot distill any secure key if you do not have secure perimeters here and there on the legitimate users. But somehow in practice it's not very easy to guarantee that the two systems are isolated. We know that these are physical systems, and it's very difficult to have perfectly isolated physical systems in nature. So just before I go on this example here, let me just summarize the security assumptions on these three characters. The nice thing, of course, is that we do not have any assumption here, and this is not even an assumption on a quantum computer. So we do not have an Eve that is using the Shor algorithm or the Grover algorithm or a quantum computer. Eve is just limited by the laws of physics. We have assumptions on Alice and Bob devices, and this, of course, is somehow the downside of the problem. But the good news is that this kind of problem is treatable. So these assumptions are held by trusted users, and we can ask the trusted users to test their own devices and to check the assumptions in the proof. So this is somehow a well-posed problem that we can tackle. Okay, so to give a little bit more detail about the boundaries, I would like to show you the so-called Trojan-horse attack. And this is somehow a sketch of a possible QKD setup with a transmitter and a receiver. And you can see it includes light source, intensity modulators, phase modulators, random number generators, and many other components. And however, somehow the question is if Eve can access these boxes. So can we perfectly shield these boxes? Well, first of all, we can see that there is a direct channel here connecting the two users. So this channel is meant to transmit information between the two boxes, so it's definitely a backdoor. And the Trojan horse attack is somehow the first attack to exploit this backdoor. So these are the boundaries that we want to guard against Eve's attack. So if we simplify the transmitter a little bit and we just leave the laser source and the light source and then the phase modulator, and then Bob is just a sort of gray box, then we can think of Eve performing this sort of attack. She will inject some light into the system using the input fiber that you have here. She will somehow have some back reflection from this phase modulator, and this phi A is the secret information that you want to keep away from Eve. And then she will obtain in the output some state that is correlated to this phase. So clearly, this is a leakage of information and is perfectly feasible in a QKD system. So rather than having these ideal 4 states for BB84, these states are correlated with some other states that Eve can exploit to increase her knowledge of, about the encoded information. So the ideal rate is this one, is this curve here. But when you consider how much light can come out of this from this box in reflection, then you can see that the bigger the light, the shorter the distance you can achieve, and somehow the smaller the key rate you can achieve. So it is very important to quantify how much light is going in and how much light is going out of the system. And then if you want to really match or get close to this ideal rate, you may want to consider additional solutions. So for example, measuring the reflection of the system through an OTDR measurement, like in this case, or you may want to add attenuators, isolators, filters here to get close to the ideal rate somehow. So these are all things that it is possible to standardize somehow. For example, the measurement to be done to measure this intensity in output of the system, or to measure the attenuation of these components. So in general, when you want to deal with criteria and certification, when you want to look at the criteria you want to use to standardize and certify this technology, QKD, you have these 3 main ingredients, the laws of physics, the protocol, and the assumptions on the hardware. And then you put them together to somehow work out a security proof. And then what you do, you test the assumption in the real system. So for example, okay, in this case, you can have the no-cloning theorem, the BB84 protocol, and you can imagine you have a single photon source. And then you discover that in the real system, a laser source is used. So at this point, you can either modify the hardware, trying to replace the laser with a true single photon source, or you can modify the assumption, trying to include the laser source in the security proof, or you can even modify the protocol, for example, and change it into something different that is more compatible with this assumption, and then you repeat this process until success. So the point, I think, is, in this case, how do we decide which assumptions to test, and how do we execute the test? So it turns out that when you know what to test, you quite easily find a way to test it. It is a little bit more difficult to find the hidden assumptions in the security proof, because they are not always explicitly stated, and they are somehow implicitly present in the demonstration. 5 minutes, thank you. So for that, I think it's very useful. Actually, it turned out to be very useful to check each of these components one by one and play Eve's role. So we talked about the boundaries, but then you can consider the light source, the laser diode, and then you can consider the phase modulator, intensity modulator, if they really prepare what you have in mind, or the random number generator, and I think Roger will say something more about that later, and then the control systems, and eventually the single photon detector that is a very tricky part of the QKD system. And for each of them, you can try and imagine what are the possible weaknesses and how Eve could exploit these weaknesses. And so you can come up with a list of possible attacks and related to the components of a QKD system and the possible countermeasures. So, for example, you can imagine that you have a laser with a multi-photon emission, and then you want to consider to perform more privacy amplification or to use different protocols to get rid of this problem or to include it in the analysis. Okay, so as a summary, because QKD systems are being deployed worldwide, we need standards and certification for this technology. And the criteria are mainly related to the implementation security. So it's not about the QKD protocol itself, but it is about how it is implemented in a real system. And today, I feel like we have several countermeasures to at least protect against the most dangerous threats, but definitely more research is needed to remove multiple imperfections simultaneously. So rather than analyzing it one by one, we want to analyze them together, all together, because the imperfections are present all together in a QKD system. And for example, in MDI QKD, you remove completely all the vulnerabilities from all the possible attacks against the detectors. And then there is big hope in this numerical approach to QKD, because in that case, you can analyze many different problems simultaneously. And then we have to test components and also the assembled modules and the countermeasures that are implemented, which could be faulty themselves. And in this case, there is ongoing work in the ETSI group that has an industrial group for standardization of QKD that somehow is doing some work in this direction. And then we also have this project that also is in that research line. And in this case, I feel an important role is played by the National Metrological Institute, which could represent the certification bodies in the next future for this technology, because they can perform very accurate measurements, and at the same time, they are quite independent bodies that are suitable for certification. So in this case, I point you to the talk by Ivo De Giovanni tomorrow that is a little bit related to that. Thank you.